This is Shuo Pang. I'm going to talk about the SOS lower bound for exact planted clique problem. Here's the talk plan. After introduction, I will quickly proceed to the proof method. And in the end, I will also provide a new perspective on previous techniques on the non-exact case. The clique problem. It is conjectured to be average case hard in the following sense. Namely, given a random graph G according to, say, the Erdos-Rene random graph model with H probability 1/2, it's hard to find a maximal clique in G efficiently and successfully with high probability. Although we almost know that the maximal clique size in G is about 2 log n, and that happens with high probability. A variant of the problem called the planted clique problem asks you to distinguish between the random graph and a random graph plus an additionally randomly planted omega clique. So far, the best polynomial algorithm can recover randomly additionally planted clique only when the clique size is roughly square root of it. And as you can see here is a huge difference between what we can do algorithmically and what is possible to distinguish in information theoretic sense. This algorithm, by the way, is the so-called spectral algorithm based on the analysis of the adjacency matrix of the given graph. As you can see, the decision version of both these problems is simply to decide the maximal clique size in G and succeed with high probability. And you can easily rewrite this decision problem as an optimization problem, and with the objective function, the clique size. Now, our main hero, the sum of squares algorithms for optimization. Let us restrict to Boolean optimization problem in the following form. A degree D SOS algorithm views everything as linear combination of monomials and relax the original problem into the following maximization, actually an SDP optimization problem. And turns out that such class of algorithms is a far-reaching generalization of previous classical algorithms like semi-definite programming or spectral algorithms. And they are much more powerful, and actually they even provide a unified insights into a wide range of classes of algorithms. As you can see, morally speaking, such an algorithm would run in time into the omega d, since it is SDP on degree no more than d monomials. And we know algorithms to solve this problem in, roughly speaking, poly into the d steps. Until Ryan O'Donnell points out that you should be careful, since in the most general setting, there is no guarantee that when running those SDP, the magnitude of the coefficients right down. They might be doubly exponentially large. Despite this subtlety, the SOS algorithm is still theoretically powerful and practically feasible. SOS can also be regarded as a proof system as the following. A proof is actually a refutation of the satisfiability of a given set of axioms, and it is one line. Such a proof is degree D if everything appear here has degree at most D. A moment reflection shows that for an optimization problem, if you can prove degree lower bound on its proof system formulation, then you get integrality gap for all degree D SOS-based algorithms. You simply add f of x equal to c as in xc. And if you can't refute it, there is an integrality gap at least c minus the actual objective value. Here is the formulation of the clique problem. Roughly speaking, the axiom says there exists a size omega clique in G, and SOS is asked to refute that. The main question is, can degree log in SOS refute this for omega equal to square root of it? You should know that for the refutation, the higher degree, the easier it is to refute, and also the larger omega, the further it is from truth, so it is easier to refute. I must mention that both parameters here are almost tight, because if n is as large as n to the 1/2, then degree 2 SOS can simply refute it. On the other hand, if d is beyond, say, 2.1 log n, then SOS can refute it for any sensible omega. Previous lower bounds. On a weaker system, we have the hardness result when omega is no more than, say, square root n over 2 to the d, which is quite good, actually. On SOS, it was proved hard if omega is no more than, roughly speaking, n to the 1 over d, which was later improved to n to the 1/3 for d equal to 4, and further n to the 1 over half of d, roughly speaking, for general d. On SOS, indeed, we have lower bound for almost optimal parameters, but only for a relaxed problem. We will go back to the detail of this relaxed problem later. Our result is a lower bound for SOS for the actual omega clique problem, which obtains almost optimal parameters. The relaxed problem is actually the following. It removes all of the equalities generated by clique size, but add a weaker inequality instead. This is often called the soft version of the problem. Why do we care about the hard versus soft? There are several reasons. First, the SOS formulation of the problem. Equalities in SOS are more useful and powerful as constraints, and algorithms can make use of them. Then to analyze, say, the integrality gap of those algorithms, you have to face the hard formulation of the problem. Second is about applications. There are concrete reductions to the hard clique problem. For example, you can simplify the lower bound of the so-called Nash welfare problem. And last but not least, it's about the techniques. The hard versus soft phenomenon actually appears in many places, with the hard case almost always left open. And people want to know why and push the limit of our techniques. I should report that in the case of random CSP, this was solved, although the situation is quite special there, since for random CSP, there are in total one family of constraints generated by one equality. However, the situation for cliques seems much more representing the essential hardness of the hard case. Namely, there are many, many more equality constraints added together. And solving them can hopefully give insights to other hard problems. For example, the graph coloring problem. Now let's talk about proofs. First, a general regime for proving SOS lower bound is to use the SOS dual. Namely, you design so-called pseudo-expectation, which is a linear map from monomials to R, such that satisfy the constraints and the non-activity condition. A moment of reflection shows if you have such an E tilde and you can prove the PSDness of the resulting matrix M, then you have lower bound. Here, since we're concentrating on Boolean case, the matrix M is simply a canonical way of representing E tilde in the matrix form. Previous methods for the clique problem. Roughly speaking, there are two main clusters, namely what I call a vertex-based method and approximate factorization-based. So the vertex-based method, as the name suggests, is mainly concerned to deal with the intersections and relations of vertex sets, and the analysis is to decompose the moment matrix into a sum of special PSD matrices called the Johnson pieces. The other one again, as the name suggests, is rather straightforward. You want to decompose M into a PSD product form of matrices. Here, what's complicated is that all the entries of all the matrices or functions are G. So in general, they are represented by Fourier characters. Now let me say something vaguely about the limitation of the methods. First, for the vertex-based one, it won't work for the optimal parameter because when omega is larger than n to the 1 over d, there is just a concrete witness of the negativity of E tilde designing this way. For the second method, the problem is that it's simply non-robust. It works only when the matrix terms have a very special product form. And as we will see later, you can't think of to simply approximate these terms so that you can make them product-like, because everything here is super sensitive to term-wise error. Matrix norm after accumulation of errors may change drastically. Now our approach to design E tilde, the starting point is to notice that the size axiom actually implies a very strong relation between E tilde xs. And we set the E tilde of xs from a top-down manner. And what's left is to decide E tilde of xs for all those d-size sets. Second, for the clique constraints, notice that E tilde xs is in general a function on G. And to make it factor through the clique function, we'd better make it so-called edge symmetric in the following form. So as you can see here, chi t are the Fourier characters of the edge sets. And by saying edge symmetric, I mean the coefficient of chi t only depends on the vertex information of t when you fix s. One more thing to explain here is the seemingly mysterious tau parameter. It's fixed a priori. And the idea is that if you want to design E tilde of xs so that later you have a good control on its behavior on size no more than d subsets, you'd better design it first on a slightly larger class. What's left is to find f. That said, let's look at the situation. No matter what f is, it turns out E tilde xs looks like that. Seems hard to say anything about it. So we'd better go back to the high level of thinking. And here the vague idea is to combine the methods, realized in the following form. Here the product means automata product. Let's look at the moment matrix. If you expand it, it looks like that. Where the U parameter means D minus A, and the size of A unit would be. Here, actually, you see a spoiler, we will take F to be that specific form later, and this expression depends on that choice. For the time being, you can just abstract it F of that. One more simplification we can do is to assume D is even and concentrate on those indices A and B of size exactly half of D. In that case, U is simply the intersection size. This is done by the standard homogeneity reduction in the presence of the hard constraints. For this matrix, notice that the parameter U depends on both I and J. It is indeed a vertex-based information. And to deal with that, we somehow want to separate it into the vertex-based part and the Johnson part. So we can express M in the following sigma pi form, where circle means the automata product, entry-wise product between matrices. And we use the Johnson-based analysis on this first factor, little mc. We can, it's not too hard to get the following lemma. How about the second factor, mc? In its expression, you will find the parameter u appears still in a very nested way. And what's bad about this? Recall that we want to apply the approximate factorization to some Recall that we somehow want to apply the approximate factorization to some part of the matrix M, in particular to MC if possible. But we need to see what is possible for that technique to be applied. Here M means MC. To achieve that goal, if you expand it, it means the second line. And to match the form, the technique heavily depends on the graph theoretic decomposition of the graph IJT for every fixed vertex sets IJ and H set T. And this implies a very basic requirement of the technique, namely the coefficient of your MIJ of the clique in MC should be decomposed into a product of local factor form. And this product of local factor form corresponds to the graph decomposition. Here's a picture stolen from our Computational course. See if the above line means the graph, and then its left, middle, right decomposition looks like that. And by local info, I mean, for example, factor LL depends only on this part of the graph, LQM depends only on the middle, and LR depends only on the right. But if you go back to check with the expression of our MC, you soon realize this is simply impossible, mainly because of the parameter U and actually A, which we will see later. Here, our idea is to sort of reversely think. Namely, if the parameter U is a big problem, then let's say we fix U first, and then reversely review I comma j in terms of the fixed R. This is realized by the following further decomposition of capital MC. Here, the idea for matrix MCR means that it contains the information of an a priori fixed subset, vertex subset R, such that the matrix is only supported on those columns and rows I and J, such that I cross J, I intersect J contains R. To work out the expression, we need the so-called Euler transform between two number sequences. And if you apply it to MCU, you get YCRA and the expression of MCR, where explicitly YCRA looks like the following. The following lemma summarizes what has been done so far. Two things to be noticed. First is that the YCRA, which appears in the coefficients of Fourier characters in matrix MCR, they are upper bounded by magnitude tau to the 5 tau. And it is essentially here where our argument requires the degree D to be no more than, say, log n over log n. And the second thing is that the good property of automatic product, namely it preserves PSDness. So in the following, we are mainly interested in analyzing the two classes of matrices, little m and capital M, separately by different methods. This is realized by two lemmas, namely on the Johnson part and on the factorization part, respectively. The Johnson part is not too hard computation, which we will skip here. And the main lemma is about the analysis on the capital MCR part. And roughly speaking, this lemma says M0R is strictly positive, while all other MCR, where C is greater than 0, can be well controlled by M0R. For the rest of the talk, we will mainly concentrate on the proof of the main lemma. Okay, as we said, the first step is to factorize capital MCR now. Here's a recast of what we will do in this step. I will hide almost all the details, but only tell you that here is some slight development of this method in our application. And let me explain a little bit on why we work with finer graph structure. Recall the goal is to factorize MCRIJT, which is the coefficient of the Fourier character chi-t in the ij position, into product of local parameters. And this is required if you want to work compatibly with the graph decomposition. But in the reality, we have that expression. Let us parse it. Actually, the second factor omega over n to the a is good. It appeared actually also in the non-exact case. The point here is that it exactly has a product decomposition where SL, SM, SR are local parameters, sort of size of the left, middle, and right part of the graph decomposition. The real problem is about the YCR part. If you look at its expression, there is no hope that you can decompose it into product of local parameters because the appearance of the parameter A this time. And our solution is, again, if we fix the pair SL-SR, then recall from this line, A is the sum of SL-SR and SM, then A would become a local parameter only depending on the middle. But of course, to really carry out this plan, you need to sort of tensor the matrix. Since you fix the indices, then there are many, many ways to fix them. And the dimension of, for example, of the middle matrix Q would be timed by tau plus 1. Now let's proceed to the step after factorization. So we finally need to prove, having got M equal to LQL, the PSDness of the middle matrix Q, which turns out to be a plus-minus combination of a family of QIs. And strategy to do this is quite classical. What's special here is actually the pseudo-random part of each QIs can be controlled by quite standard treatment, namely the norm bounds on special random matrices, graphical matrices. The harness here is about the structural part, and its analysis is highly non-standard. Recall our choice of the function capital F in designing etude. I should say then its main purpose is to serve this step. After standard manipulation and error controls, it finally boils down to prove the PSDness of this sum of matrices, where each H and T is very, very special in the form that they look like a factorial. Let's try to analyze this H and T. In general, such a matrix whose entry only depends on the sum of their indices is called Hankel matrices. And such matrices in general are super singular in the sense their spectrum is very, very spaced. In particular, this is a serious problem if we want to prove the plus-minus combination of a family of such matrices. However, in our case, everything turns out to be even more special. And let us term the matrices HMT factorial matrices. As in the last line here. A surprising observation about this factorial Hankel matrix family is that they have a sort of stable diagonalization, and I will explain this. Here is a simple example at the case MT equal to 2, 2. The matrix H22 on the left-hand side can be diagonalized as the right-hand side. Now if you raise T to be 3, then H23 can be diagonalized as this. The point is that there is a relation between the side matrices of the two cases. Namely, they differ by a factor of the lower Jordan with all 1 on the diagonal. In general, we have the following lemma about this family of matrices. It's a generalization of the observation we just had about that example. And from this lemma, we can prove a special combinatorial result. And from there, we can conclude the PSDness of the desired matrix. Now, a summary and reflection of our approach. First, conceptually, it is simple. We want to find ways to combine known techniques. And technically, of course, everything here is super technical. The one point that I want to highlight is about the choice of the function f in the very beginning, where we design our etude. A posteriori semi-intuition is that if you do reverse engineer to see what condition you need on this f, then you realize it should be somehow strongly convex, in the sense that even after drastic change, like the Euler transform and plus minus combinations, these matrices still give you a PSD matrix. But still, even having this semi-intuition is far from enough, because in the actual analyses, we encounter the factorial handlers. And their analysis is super special and ad hoc in a sense. And my question is this encounter accidental or is it necessary? Or more simply put, are there combinatorial explanations of the design of F, or are there simply any other choice? This finishes the second part of our talk. Now let's go back to the solve problem and provide the promised different perspective on the techniques there. A problem recap and its technique recap. A remark here is that for the design of etude, unlike the hard case where there are very rigid restrictions, so the etude must take some very complicated though specific form. Here, you can use a softer but canonical idea, namely your etude indeed tries to simulate the Planck clique setting with some twist. And the analysis uses approximate factorization. What's new? Our initialization happened on both parts. For the first part, we give a new but still canonical way of defining the pseudo-expectation. And the point here is that our reasoning is mainly based on vertex sets using linear algebra instead of edge sets. And for the second part, I think the point is that for the approximate factorization, although it's conceptually simple, you want to decompose your matrix into LQL form, but the actual realization is extremely complicated and deeply depends on the use of a graph theoretical decomposition. And the question is, how to come up with that theoretical graph theoretic decomposition and the realization of the need of that. Here I used a method called the moderate analysis to sort of resolve this problem. It's just a sort of dimensional analysis using the known matrix norm bounds, and actually give you very strong hints and leads you to the use and realization of that graph theoretical decomposition. Here are some open problems after this work. This concludes our talk. Thank you. Here are the references.